Uh, so, hello everyone, welcome back again into another topic on linear algebra for machine learning. In the previous video, I talked about Sherman, Morrison, Woodbury identity, and what I'm going to do is discuss a special case of a Morrison, Woodbury identity called a Sherman Morrison identity. Essentially, what's happening is if we take a special case of UV, these vectors, where um, we replace this U and V matrices with the one rank matrix, uh, then it becomes a U and V becomes vector. So for example, if U in the previous one, if U were an n by k matrix, now k becomes 1. So this is if A is an n by k matrix, if A is an n by n matrix, then U becomes, let's say, n by 1 matrix, and V also is an n by 1 matrix. So U transpose becomes 1 by n matrix. So we can add these two matrices, and this becomes a special form of Woodbury Morrison Sherman Morrison identity. So what we are going to do, and note that in that case, this particular thing in denominator, it becomes a scalar. So, and it's not a matrix. One is just a scalar you are adding. So for example, this one is a 1 by n matrix, and then A is n by n, and so this multiplication will become 1 by n, and then you multiply again with U, which is an n by 1. So essentially you will find that this is a 1 by 1 or simply a scalar. So this whole thing will be divided by a scalar, let's say k, and that will give you a simplified expression. Now let's look at an important an interesting example, and that comes from a book on linear algebra from Charu Agarwal, a very important book. But let's say I will let you do an example on your own. I will leave it for an exercise for you to apply this formula to see that you are able to find this find the inverse of this vector, where B is given by this, and you can take U as some other vector. Okay, but I'm going to do some important example. I will leave the other examples in the exercise in the link in the description. An important thing is, when you do study such kind of things, do attempt some of the problems. So we need to use the Sherman Morrison identity. We are given a huge matrix, a 10 by 10 matrix, which have ones in every single entry, in every single in every single of its entries 1, other than the diagonal matrix has 2. So how does this matrix looks like? So the matrix will look like something like this, which has 2 here, and then 1 all ones, and then again 1, and then 2, and then all again ones, and so on and so forth, and in the end we have 1 and all of things. So all those diagonal elements are 2, and we want to use this identity which looks like this. I'll write it here as the first thing we want to go about this is, so let's write this and then try to solve this. Is I'll write this matrix A again as 2 1 1 1, and all the diagonal elements are 2's, and we have 1 here. I can write this matrix, if you look at carefully, as a sum of the two matrices. One is, I break it up so all the diagonal elements are 1. So this is an identity matrix, and then there is another matrix which has all entries as 1, and these are the 10 elements. And the rationale for doing is that we are trying to make this A matrix as this identity matrix, and this matrix I'm trying to write as a product of two one rank matrices U and V. So I can write it as I matrix plus, if you look at carefully, this is nothing but a product of two matrices U and V T bar, where each of U will be given by 1 1 1, this thing repeated 10 times, and same is V, but V transpose becomes 1 1 1 1. So this is an n by 1 matrix, and this is 1 by n matrix. If you multiply these things, you get an n by n matrix, which is this one. So if you now apply the this formula, then this formula is, I'll rewrite it, A plus UV transform is equal to A inverse minus A inverse U V transform times A inverse and this whole thing divided by 1 plus it's let me look at V transform A inverse U, and then the key idea from here is A is nothing but this identity matrix I, so I can write it as I inverse minus, and then again I inverse is again I, and UV transform A inverse is again I inverse, so that becomes I can write it as U into V transform divided by again A inverse is identity matrix, so 1 plus V transform into U. Now this I can write it as, and of course, and this is I minus this whole thing, I minus, and I inverse is again I minus, what is UV transform is nothing but this 1 1 1 matrix. Let's call it X matrix, I minus X divided by, now V transform is this matrix 1 1 1, V transform, this is 1 1 1 all 10 times multiplied by this 1 1 1 1 matrix. This is simply a scalar, you multiply these 1 1s with 1 1 1, so 1 into 1 plus 1 into 1, etc etc, this becomes 10. So 1 and plus 10 it becomes 11. So how does this matrix looks like? So the matrix will look like this, all ones here minus, now I minus X, this identity matrix I minus this X matrix will look like this all are zeros, and then all these entries are minus ones, and this whole thing is divided by 1/11. So if you want, you can try solving like this and arrive at a solution, but this could be an interesting kind of problem to solve. I will have more problems in the description for you to try, just to give you an idea. I hope you enjoy. understanding about Sherman Morrison identity. By doing these kind of problems, you will have a better chance of understanding it and then applying it somewhere. Thanks for taking a look.